Yeah, I'm never gonna hear that. That's a
Presentation.
yeah, all these things happen. Relationships evolve over time.
Okay, you good? You good?
Yeah.
Okay.
No, that's a question that's coming up. Yeah. Yeah, it's coming. Oh, my pleasure.
All right, greetings, everyone. Hello, greetings. Thank you so much for joining us. It's a real pleasure and honor for me to welcome Professor Robert Davis, who's one of our distinguished alumni who left UD in 1988 with his doctorate here, and then has been on the faculty at one of America's leading public universities, University of Virginia, for the past 30 plus years. 38 years.
38 years.
And
I'm the longest tenured person in my department. I
so,
felt like I just got there yesterday. I mean, for decades, probably.
so it's a real treat for us to welcome him, and it shows the impact our alumni have had on education across America and the world. And Bob has been exemplary, not just as a researcher, but as a teacher. He's won several awards for teaching. From the AAG as well, he's twice been awarded for the climate specialty group in various fields, and with the American Meteorological Society as well. So he's a role model in so many ways for our students, for our other faculty. So thank you for coming, Bob. Please take it away.
Yeah, you're so kind. Thank you very much.
I'll manage this, don't worry.
Do I have I can advance with this? Or?
Actually, this is the better way to
Okay.
just use the arrow.
Okay,
Yeah.
fantastic, thanks. Yeah, it was odd driving back here today because I probably hadn't been here for, I don't know, 30 years or something like that. And I'm like, I've been to Delaware a few times, but I didn't like come back to the university, and it's like shocking. I'm like, okay, nothing looks at all remotely the same. And like, got to College Avenue, I'm like, okay, finally something that looks familiar. But we were in Robinson Hall when I was here from 1982 through 1988. And I guess you moved here not too long after that. So thank you all for coming. It's a real honor to be back in the department again. And thanks for the invitation. So what my story is that when I was an undergraduate, I was a meteorology major at Penn State. And I was talking to my advisor. I said, I'm really interested in how weather and climate impacts people. Not much how people impact weather and climate, which of course has been the major issue that we've been talking about for the last 30 years or so. And it turned out that at the time, there was a group of faculty in this department that were working with a group in NOAA on sort of human impacts. And it ended up just sort of being perfect timing for me because that was something that I was really interested in. And I did a terrible, embarrassing master's thesis that you don't need to read, but you can look up in the library. I did some synoptic climatology stuff in my PhD, but after I got promoted, got tenured, I started getting back to the issues that really inspired me at the beginning, which was climate and health. And so what I'm going to do today is give you sort of an overview of this topic in terms of my perspective of the research that I've been doing. And our time is an hour, or
We have 75 minutes total.
but you want me to go about 45?
Yeah, 45 for
Yeah.
then discussion.
Okay, and that'll be perfect. So I guess we'll leave questions for the end unless you want to do it. I mean, I'm open.
Yeah, I think points of clarification you can ask right
However you want to do
away,
it.
but otherwise more detailed questions, let's wait till the end.
Fantastic. Okay, so this is a time series of mortality in Philadelphia over some period of time, 83 through 2008, it turns out. And this is smooth with the 21-day moving average smoother. So it's just smooth mortality. Okay, just daily deaths. Now, if you superimpose January 1st on the time series, you can start to see there's a relationship there. A lot of these peaks tend to occur on around January 1st. They're winter time peaks. And if you also look sort of in midsummer, there tends to be troughs, which suggests that the mortality, there's a
What
picture.
happened there?
Hello.
Okay.
We're back. Okay.
Yes.
Is there any way you can, I think you
Yeah, I
can
was
make that
trying to
disappear?
get this.
I
That's
think
what I
if
was
you go
trying
up
to
there. Under more, there's
More,
and it's hide floating meeting controls.
there we go.
Ah, there. And now if you can get rid of that, my aesthetic is completely blown by these.
Yes.
Okay, now we're talking. And now we can't do anything. We'll just look at this slide for the next
No,
45 minutes.
There we
Okay,
go.
there we go. Right. So, the question is, are there associations between the seasonality and mortality and temperature? And we're going to talk today about the nonlinearity of these relationships. So there tend to be seasonal relationships, but it's complicated. And you also see it inconsistent, it's inconsistent at various times of year. In other words, extreme heat, we always think it's high mortality, but it's occurring at a low mortality time. If you were just to correlate temperature and mortality, you would get a strong inverse relationship, but nobody is going to argue that extreme heat is good for people, right? So things get complicated when you just try to do that sort of relationship. Turns out that cold winters aren't necessarily deadlier than moderately cold winters. So when you get into the details, things start getting interesting and kind of complicated. Just to give you a sense of this, here's a couple years. Once again, daily mortality happens to be Philadelphia with the smoother through the data. And I want to highlight a couple things that are departures from the seasonal curve here. First of all, mortality is seasonal. So why is that? This is doesn't work on that kind of screen, right? Why is mortality seasonal? Secondly, look at these large excursions from the seasonal curve. What's causing these excursions? Also, why does the seasonal peak timing vary from year to year, right? What's going on with sometimes we have a peak followed by a trough, and other times we don't. And what's happening when you compare summer or autumn and spring, okay? So there's a lot of interesting kind of nuance here that is departure from what I'm calling the seasonal curve. So this will be our basic graph that we'll go back to. And we'll keep coming back to this during the talk. Mortality versus time over a course of a year and a half or so. Winter peak, summer trough. What I'm interested in are these excursions from that seasonal curve. What I'm calling the smooth yellow brown curve here with interesting anomalies. As we're going to find out, many of those anomalies or departures from that seasonal curve are related to climate. And that's what we're going to be working through today. By the end of the talk, you'll have some understanding of how health varies over the course of a season, over the course of a year, over the course of 4 seasons, based on some research that I've been doing. Okay, so that's our context. Now, without getting into the details of this, our body is always responding to our external environment. When we're getting indirect sunlight, we're getting radiation from our surroundings, we're emitting heat to our surroundings. You walk from outside into an air-conditioned building, all of a sudden your brain starts doing things to your body, reacting to that sudden kind of temperature change. You're always in this sort of flux to try to reach a sort of stable condition with your external environment. And so our body is always, you can think of in flux in that respect. It's always in sort of a sense of disequilibrium. Now, this is a reminder that our species, Homo sapiens, is a tropical creature, right? We evolved in the tropics and subtropics, and of course spread out over the entire planet eventually. But a healthy body core temperature is 37 degrees. Heat death varies depending on who you talk to, occurs when the core temperature is about 42 to 45 degrees Celsius. However, cold death typically starts about 27 degrees Celsius. Our average condition is dangerously close to heat death. In other words, the body core temperature is not over here. Why is that? Well, it's because the human body does a great job of dissipating heat, but we have a terrible time of generating heat. Okay, so cold, on average, is generally much more dangerous for the body than heat is. So when we are experiencing low core temperatures from exposure to a cold environment, improperly functioning thyroid or other possible reasons, how does our body deal with this cold condition? Well, of course, we can wear clothes, right? We can generate indoor heating. Of course, we can adapt. But our human body actually does things beyond those sort of adaptations. The thyroid can release hormones that will increase our metabolism. We can generate more heat. Of course, we can shiver. shivering or thermogenesis turns out to be a very costly energy usage for the body, but it's a way to generate heat in emergency conditions. Or we can have vasoconstriction, which I'll just talk about in just a second. But maintaining a core temperature in a cold environment is energetically costly to the human body. It's very challenging to our organ systems, and so we try to avoid those situations as much as possible. Now, vasoconstriction, you probably know, this is an artery or vein, going from the heart to, and then vein going back to the heart. And there's some capillaries coming out close to your skin, right? So what will happen when we're in a cold environment, the hypothalamus will tell your body to constrict the blood flow to the surrounding skin, right? And what that does, yeah, go ahead.
Sorry to interrupt you, but I was wondering whether your theory will be applied to people that live in Nordic countries, in the Nordic countries.
Yeah, we'll talk a little bit about
Because
adaptation.
37 in Scandinavia is too hot.
Well,
37 degrees Celsius.
well, 37 degrees, oops, going the wrong way. Yeah. 37 degrees is the human body core temperature. That's your sort of rectal temperature, right?
Yeah.
And that is true across all human beings across the planet. Now, your skin temperature is going to generally be quite a bit lower than that, right? But that is average core temperature for Homo sapiens. Is actually a little bit lower than that. Okay. So
Yeah, that's
Yeah.
98.6.
98.6, that's the number, yeah. Yeah, so the advantage of this vasoconstriction is that you don't want the blood flowing to your skin and then having heat dissipating through conduction to the surrounding environment. So colder blood would be flowing back to the heart. In a cold environment, the main core goal is to keep the heart and the brain and the lungs functioning, so to keep them warm. What's the cost of that? Well, the cost is blood flow to your fingertips, to your nose, to your ears, to your toes. And then, of course, you have frostnip and frostbite and all the implications from that. So, but this is the body's response to try to keep you alive, and we might lose a digit or two in the process. We also have, kind of interesting, don't think about this, but what's called countercurrent heat exchange. So this is an artery going, let me just put the heart up here. Here's the heart. You have blood going from the heart to across the body, and then you have blood flowing from the veins back. And so when the arteries and the veins are in contact with each other, there can be heat exchange across those, right? So you see what's happening is you have higher temperatures of the blood close to the heart as opposed to out in the extremities. And that countercurrent heat exchange allows you to have little fellows like this who can survive brutally cold conditions in the Arctic, because there's almost no blood flow to the feet, and they can keep the main core warm because of this countercurrent heat exchange. Okay, so that's what we're happening in cold conditions. Obviously, in warm conditions, from exposure to a hot environment, overeating, exercise, etc. The response, of course, is sweating. Now, you probably all know sweaty people. You might be a sweaty person. I'm going to tell you today, this is something you should be proud of. You should say, people, hey, I really prolifically sweat, because I'm really good at releasing and cooling my body off in hot environments. No mammal relies more on sweating for heat dissipation other than human beings. And we can also have, there's a little quote I found. There's no one human attribute more important than the ability to sweat skillfully. Now, I could argue there might be a few things that might be more important than that. Put that high up on the list, probably top 10, right? So now in the case of the exposure to a hot environment, now we have what's called vasodilatation, where the blood vessels will expand, allowing more blood flow to the extremities of your skin, right? And so that heat will then evaporate sweat from your skin, your body cools off, and then you have cooler blood flowing back to the heart, right? So our body is always going through these sort of small scale changes, so we're adapting to these different environmental conditions. Now, in a study I did, now it's a couple decades ago, what we did is, one part of the study is we compared December, January, February deaths in US cities, this accounts for about 60% of the US population at the time, to summertime deaths. And all deaths are categorized according to what's called a major diagnostic class. There are about, I think in this case, about 18 different classes or so. Basically, they're organized by organ systems. For this particular figure, if the red bar goes to the right, that is more prominent in the summer, in the winter, excuse me, and if it goes to the left, it's more prominent in the summer. And you can see that almost all causes of death are higher in the winter. The four main causes of death are cancer, circulatory, respiratory, injury, and poisoning. Cancers basically show almost no seasonality whatsoever. Injuries are slightly prevalent in the summer. You can sort of imagine why. The main difference we see is for respiratory disease. Fully 50% more respiratory disease in the winter than in the summer. And circulatory is also quite a bit higher. So the question then becomes, is this seasonality somehow related to climate? So, which brings us to influenza and pneumonia, okay? This is a plot of all-cause mortality on the bottom for the United States. This is not my paper. It goes back some period of multiple decades. Oops.
Oops, sorry.
That's okay.
We got a message that the screen is not shared. I don't know,
Oh,
the
okay.
Zoom people.
All right.
Screen is, okay, presentation. Is it working now? Let's see what happened with it. Let me try one more time,
That's
because they're two separate ones. Let me see. Could the zoomer say, is this showing now? Can you see the slide? Yes, no? In the chat? I can see the screen fine. Okay, I can see it now.
Great.
Okay, good. All right. There.
All right, no problem. No problem.
Okay.
All right. So you can see the same kind of seasonality I was talking about before, right? In terms of total mortality. On top is just influenza and pneumonia, and these diseases are linked because people that get flu oftentimes get pneumonia, and it's hard to tell if they actually had flu first. Oftentimes they don't test for that, so they're linked together, right? If you get influenza, you're most likely, if you're going to die from that, it's going to be from pneumonia that is related to that. It's comorbidity. And so you can just do a visual plot, look at that. You can see, boy, it certainly looks like the overall mortality death rate is highly linked to pneumonia and influenza. The peaks really match up. And in fact, in this particular paper, a gentleman named Reichert and his colleagues, they looked at a number of different causes of death. Here is heart disease, cancer, there's this pneumonia and influenza, cardiovascular, diabetes, and everything except cancer sort of tracks in terms of the time series along with the influenza and pneumonia deaths. And so they made the statement, and I like when people make bold statements in papers because it makes them interesting. We believe that the singular cause of excess winter mortality is in fact influenza, okay? Now, around this time, there was an influenza expert, a pneumonia expert, kind of came to UVA and we're talking about the seasonality of influenza. And they said, we really don't know why it's seasonal. And it seems like a huge question because it's so intimately tied to when those people die. They're trying to figure this out. Around that time, a paper came out. Well, let me just, a little bit background of influenza first, just to give you some numbers. 36,000 annual deaths, 250,000 hospitalizations, 500,000 deaths annually. And of course, it's spread via aerosols that carry the influenza virus. It can be, you can get it by directly contacting the virus, or it can come from the air. So it can be ingested in your nose eventually, or your mouth. Number of different methods. Okay, and here is just to talk a little bit about the influenza seasonality. So in this particular paper, the blues are showing winter months, so December, January, February. The warm colors are showing summer months. We're looking at the United States here. You can see the seasonality in blue. Go down to Mexico. You can see it's a little bit more muddled. Colombia, not a heck of a lot going on with the yellow there. Get down to Argentina, and of course that's the purple, right? So it's a winter peak, regardless of where you go. in the northern hemisphere, or across from the northern hemisphere to the southern hemisphere. In fact, that's how the flu virus for each year is determined when you go and get your flu shot. The flu virus is always evolving and mutating based on what kind of defenses it's encountering when it tries to attack your body. And so right now, the people in the southern hemisphere in Australia and Argentina, they're tracking our flu and they're developing the flu virus for their season. And then we'll be tracking their flu. And we're always sort of trying to beat the virus, chasing it as it bounces back and forth from hemisphere to hemisphere, from winter to winter, right? So the study I was talking about, they had guinea pigs. Apparently the guinea pig lung has a lot of similarities to the human lung, according to my respiratory disease friends. This paper came out in 2007 and got my attention. What they did is they had guinea pigs in cages, and they infected the upwind guinea pigs with an influenza virus. They had the airflow showing that the downwind guinea pigs would get airborne transmission of the flu from the upwind guinea pigs. And they, of course, changed the environmental conditions in the chamber. So they altered the temperature and the relative humidity to see what the infection rate was for the originally healthy downwind guinea pigs. Kind of a straightforward sort of animal laboratory experiment. And here are their results, okay? At temperatures of 20 degrees Celsius, you can see they changed the relative humidity here. At low relative humidities, the transmission rate was 75 to 100%. At low temperatures, 5 Celsius, transmission rates were from 50 to 100%, okay? At higher temperatures and lower relative humidities, nothing. And so they suggested that cold and dry air was associated with the higher likelihood of downwind transmission for the guinea pigs that were originally healthy. And there's a number of reasons to think why this would be true. The influenza virus survives low relative humidity conditions indoor much better. It's more stable in cold and dry air. It survives longer on cold surfaces. The aerosols in the air remain in dry air a longer time, so there's more opportunity for you to ingest them or inhale them. As our nose and our nasal passages dry out, the virus can get in deeper into our respiratory system and make the possibility of infection likelier. So to some extent, our body's defenses are, a little bit more challenged in dry air. And then, of course, people in the wintertime spend more times indoors, are in closer contact with each other. And so there's a human component here as well. And a lot of times people don't humidify their homes in the wintertime, and the air tends to be drier inside. And I think it's important that, especially when we're trying to deal with flu, that if you're heating your home, you're also trying to humidify it in the wintertime. That really helps with disease transmission. There's also a theory about children returning to classes in September that a lot of people talk about, but nobody's ever looked at it. And I think it's kind of unlikely to be the case. So given all this, I'm thinking, well, maybe we can account for all or part of the sort of year-to-year variability in deaths by studying the climate effect on influenza, right? Seems logical, highly seasonal, and we have a reason to look at that. So what we're looking at here, we hypothesized that cold and dry air or cold and dry seasons would enhance mortality, and that it would vary within the year, whether you had sort of cold and dry weather that was within that year that might result in peaks. And we'll take a look at that next. So the problem here, that's kind of a problem with all of this research, is there is an unknown and a variable lag between the infection and the subsequent data that we get. And I'll explain that to you with a simple example here. Let's say that I believe that day 1 is the day where infection is likely. Let's say this is a cold and dry day, okay? So what kind of data do we have? Well, patient number 1 comes along 2 days later. It takes, you might get the influenza virus in your lungs today. You won't see symptoms for 2 to 3 days, right? So somebody gets sick on day 3. Okay, then it's like, okay, I've been sick for a week. I'm going to go to the ED. Maybe I'll be admitted to the hospital. Okay, that happens on the 9th. And then maybe this person passes away on the 19th from that. So what data do we have? Well, we have a hospitalization, one count on the 9th, and we have a mortality count on the 19th. Those are the two data points that we have. We don't know when the person was infected. We would never know that, right? Okay, but we have some data. Here comes patient number 2. Maybe they're infected on the 4th from that same weather event. They immediately go to the ED and then they die a day or two earlier. And so 2 more data points, right? Here's patient number 3. Got sick the next day. This person's a man, so they stayed away from the doctor for 2 weeks until their wife finally told them to go to the hospital. They go to the hospital and they die a few days later. Okay, another data point. So here's the problem you see is I'm suggesting that something happened on the 1st that produced this very disparate response. We're not going to see a clear one-to-one relationship here because human beings behave the way human beings do with free will, and they all react differently to the same sort of input of disease, right? So how do we handle that? Well, we have to use smoothers and lags to sort of deal with this sort of complex relationship in our response variable that we have here. So just to give you an example, I generated a synthetic data set with 200 deaths that peaked on the 17th, okay? So there's no deaths, and then we have kind of a peak in the trough. This might reflect the kind of data we would get for influenza mortality. So if we smooth the data by using a centered smoother, it's going to have the peak mortality sort of right around the middle of the data set here, where, this is a centered 17-day moving average. So we're taking 17 days and averaging it through the data, and that's what you get. Now, to deal with the lag, well, I'm suggesting that what caused this was on the 1st, so we can make this a leading smoother. And now we can take this data set, shifting it 17 days this way, try to correlate that with climate and see if there's a relationship, right? So we're building in smoothing and lagging to account for these 2 problems. And I'll give you an example here of a study we did in New York City, where we had a long time series of influenza and pneumonia mortality, okay? This is standardized z-scored mortality. So the average is 0, the standard deviation is 1. There's the line showing +1 standard deviation. And then this is with that 17-day leading smoother that I just talked about. And so what we can do over the course of this period of record is we can identify high mortality episodes in New York City, as indicated by all the green arrows there. It happened a number of different times. Some years it didn't. Some years there were multiple peaks, et cetera, right? And we can examine those data and compare it to climate data. So I think this is a pretty interesting plot. The blue line is this leading smoother mortality, okay? For 1980, 1981 through 1985 in New York. The red line is smooth dew point temperature. It's a moisture variable for the atmosphere. And if you look at the times that we have peaked in flu, you'll also notice that there tends to be lower dew point temperatures over that period of time, right? And they should match up because we're accounting for the lag here. You see high mortality, dry air. 1981, big flu peak, corresponding with the period of dry air, low dew point temperatures. Even this little peak here, boom, boom, right? It actually kind of works out too well. I looked at this data, I was sort of suspicious. Look at 1983, no flu peak, no period of rolling dry air either, right? And there's one more in 1985. So without doing any kind of fancy statistical analysis, other than this sort of simple smoothing, I think you can be visually convinced that it seems to be the case that after you have a period of dry air, about 17 days later, there's a peak in flu deaths, at least in New York City, right? And there's reasons to think from the slide previously, why there would be a cold dry air linkage to influenza. And we've seen that. When we did the analysis, if we looked at dew point temperature versus mortality and duration, we find a strong sort of inverse relationship between them. So it seems that when you have cold periods, dry periods in the winter, that during that period, the likelihood of influenza virus being transmitted is enhanced. And we then looked at other cities. You have 5 different cities here. We sort of found the same result. Here we're comparing during P&I events, the bar on the left versus the sort of average on the right for different cities. And we found the same kind of relationship. And I'm certainly not the only person doing this research. There's a whole community that over that same period of time has found kind of similar relationships, not so much in the tropics, but in the middle latitude countries where you find this kind of linkage between cold, dry air and influenza transmission and mortality associated with that. So I'm not suggesting that that accounts for all of this peak, but at least some of it is probably related to cold, dry air in the winter and the associated mortality that from the influenza that's associated with that. All right, so let's move our attention now to the summer. Okay, this is a plot. Goes back a long time. This is the kind of, you get excited, you get all your data, you throw it down there and you get a blob. You're like, I'm never going to get tenure now, right? But there's a lot of kind of interesting information hidden in the data sometimes. This is daily mortality versus apparent temperature. Once again, we're using Philadelphia as an example. It's afternoon apparent temperature. This is the heat index, temperature that combines air temperature with relative humidity, sort of how the body feels during hot days, right? So if you actually look at the data in detail and look at an average as you sort of work through the data over smaller sections, you get a U-shaped relationship, okay? This is for the entire year now, all data for multiple years in Philadelphia. Generally, when you have sort of normal sort of average temperatures for your climate, you're having low mortality, but you have a little bit of a peak here at higher temperatures and a little bit of a peak there at lower temperatures. A U-shaped relationship, sometimes it's sort of J-shaped, sometimes it's an inverse J-shape, but this is what we found for Philadelphia. Well, if there is any sort of, there's very little in this discipline of human biometeorology that we say is generalizable to all populations and all people in all countries. This might be one of those few things. Here is what it looks like in Croatia. You can see there's a little bit of a peak there in the heat. This is the plot in Thailand, okay? J-shaped relationship. Here we have Spain, cold cities, mild cities, warm cities, U-shaped relationship. Here we are in Mexico, pick your city, U-shaped or J-shaped relationship, wherever you look. Here's Bulgaria, right? I could go through the list of the literature, and when you plot up some temperature variable versus mortality, it's probably going to look like a U or J shape. In other words, we're really interested in what are happening at the extremes of the distribution, the high temperatures and the low temperatures. England and Wales, pick your year, right? So that certainly was what we find. This is research that I was talking about before that we did a little bit of back when I was at Delaware, and this was subsequent work I did at UVA. Here we're looking at New York City, same kind of blob of points. If you remove the seasonality, because we know there's inherent seasonality in the data that that probably isn't partly is related to climate, but mostly not, right? When you deseasonalize it, you can then sort of look for, in this case, at the higher end of the curve. There's our U shape, remove the seasonality. And what we can do is we're focusing here on this uptick that we see in New York is we can find the temperature beyond which you start seeing a statistically significant increase in mortality. And we could call that the sort of heat threshold temperature. And you can say, well, based on the data for New York City, 30 degrees C, afternoon apparent temperature seems to be that value, right? Well, you can do that for different cities. And the geographers love this because this is showing you that there is adaptation or acclimatization based on where you live, which should be a shock to no one, right? The threshold apparent temperature in Minneapolis is 40, is 30, but it's 44 in Phoenix, right? Obviously, the people in Phoenix are adapted to heat, otherwise they couldn't live there. Everything's air conditioned, right? You're not spending time outside, there's a lot of shade when you are, etc. But lower threshold temperatures in the Northeast, in the north part of the mid northern here, right? And higher threshold temperatures in the South. Now, back when we first did this research, I was working with Larry Kalkstein. This is the first paper I actually published. We published it in 1989. This is work that we did in this department. We were the first people to suggest that the threshold should vary based on location. At the time, the National Weather Service said, when the temperature gets to X, issue a heat warning. It was the same warning sent out in Maine and in, Phoenix, right? Doesn't make sense. Phoenix was under a heat alert from like May to September, right? So anyway, there's obviously the adaptation from one location to another varies, or what we call the acclimatization, right? So I'm now talking about a physiological adaptation, not just sort of the behavioral, structural adaptation, but an organism is when you're exposed to environments of hot and cold, it produces strain from those environmental stressors to our body. And if you are acclimated to heat, so this is studies on, physiological studies on people who are well acclimated, they have lower heart rates, lower metabolic rates, lower skin temperature, they sweat more, we were talking about that before, their sweat is more dilute, there's more blood flow to the skin, more vasodilatation, right? And the decrease in perceived exertion in hot environments. So you can heat adapt if you wish, or if you're exposed, even if you don't want to, you're going to do it. Exercise hastens it a little bit, but if you're exposed a few hours a day over several days per week, over a course of weeks, your body is going to adapt. So that means that when we're going from spring into summer, our bodies are going through this acclimation process. And by the time we get into July and August, we're going to deal with heat differently than we did back in May. The same weather conditions are going to be different because of this acclimatization. And the same thing, it's kind of interesting. Research shows that it's easier to move from a hot desert to a hot humid tropics and vice versa. So the direction matters, apparently. Now, the rate of acclimatization, people talk about this, and it's kind of one thing that we're really not clear on, but research currently is suggesting several days to several weeks, and that once you're adapted, it will continue for a month without continued exposure, okay? But the benefits are lost after about a month of non-exposure to that environment. Now, going in the other direction for cold, it's not nearly as clear as the research is for heat. Generally, the best thing for the human body to do in cold is to avoid a cold environment, because remember, we can't handle it very well. There's some relationship to the onset of the temperature at which shivering will start. People will have less vasoconstriction if they're sort of adapted. There's effects on blood pressure, heart rate, and perceived exertion, et cetera, the same as before. And it turns out that a person who adapts well to heat doesn't necessarily also adapt well to cold. Some people are better heat adapters. Some people are better cold adapters in terms of their biophysical acclimatization. So, obviously, we'd expect a difference in different cities because of differences in acclimatization, right? We found that. Now, in this research, I was asking the question, what are the trends looking like in heat-related deaths? This goes back a couple decades, actually. What we're looking at here, the first bar is the 1960s and 70s. The second bar is the 1980s. The last bar is the 1990s. We published this in just after 2000. And you can see that in almost every city, there's clear evidence of adaptation. Fewer people are dying from heat given the same exposure than they were decades earlier. And obviously, this is related to a lot of different factors. It could be more awareness of heat. Certainly, there's more influence of air conditioning penetrating more locations. But if you have air conditioning and you can use it, it's going to certainly help you from heat exposure, right? Now, to just follow on that research. So if you think about, let's say this is a distribution of the vulnerability of a population of people, okay? And a heat wave comes along and you're going to have heat-related mortality. The most vulnerable people will generally be affected by extreme heat. So what's left behind is a healthier population, right? Their bell curve has changed here, right? So if we have a subsequent heat wave, because the remaining population is healthier, they're less likely to be affected by it. And this is, it used to be called, the effect was called harvesting. And that's an unfortunate term, very politically incorrect. Nobody wants to say their grandmother was harvested by a heat wave, right? It's just, so we call it now mortality displacement. So the notion, the politically correct term is always more complicated than a simple term, right? But I get it. Who wants to call it harvesting? So the notion is, you have vulnerable people, probably that were going to die within the next week or so. A heat wave comes along, poof, they died a week earlier, right? That means that you would expect a peak, but then it could be followed by a trough because the remaining population is healthier, and it's going to take a while till you have more elderly, feeble people that go onto the bell part of the curve there. And we see this response all the time. In this particular study, this is the three-dimensional plot. Think of the vertical axis here as mortality. This is lag 0 through lag 20. There's our U-shaped or J-shaped relationship that we talked about before, right? So there's heat-related mortality. You can see high temperatures, bottom right at 0 lag. Look at this. See this dip at about day 6? That's mortality displacement. On these days, there are fewer deaths than expected, for that particular time of year. And so we decided we would like to investigate mortality displacement because when people write papers, they count the deaths, but they don't count how many of those deaths were about to occur anyway. Obviously, because you don't know what they were, right? But most of these counts, if you don't account for mortality displacement, are overestimates. If you believe that mortality displacement exists, right? And we can get into the literature on that. But what we decided to do was investigate it. And so the way we went about doing that was, here is apparent temperature, 0 right there. So these are anomalies, so they're departures. Here's mortality anomalies there at the bottom. Of course, we're looking at the warm season here because we're interested in heat. Okay, so what we can do is we can say, let's define a percentile. Here we're saying the 80th percentile is going to be about 2.5 departure units, right? And we're going to look at heat waves. So we're going to say, let's look at 3 consecutive days above that threshold. Identify all those cases. And let's say, okay, here's one. Let's look at the mortality record that starts on that day. And now we'll calculate mortality displacement, which would be for the next 2 weeks. We have to pick the time lag. We're going to count the sum of the positive anomalies. Those would be the deaths. And then the numerator would be the sum of the negative anomalies, or what my student who worked on this called the negative deaths. Now, I have to wrap my head around the concept of a negative death. Other than like a zombie apocalypse, I don't know what a negative death would be. But you get the idea here. These are anomalies. These are days where there are fewer deaths than you would expect on that day because we had potentially a heat event. And so now we can quantify it. We can then change the threshold of the percentage to say, as that you pick a more extreme threshold, how does the ratio of those sums change? And we can plot that up for different cities, for different thresholds. We did this for about 7 different cities. And you can see that all these values, some of them are like 100%. 100% means that there is no heat mortality whatsoever. Those are all displaced deaths. 50% is about the highest value we got for Philadelphia, which said that means 46% at a threshold of 97, at the 97% threshold, 46% were heat deaths, 54% were displaced, okay? So the notion here is that if you don't look at this trough that happens after the peak, you're probably overcounting the number of deaths that are actually related to people that wouldn't have died anyway in the near future, is the way to think of that. So, winter flu, heat mortality, mortality displacement. Now we're starting to see some of these sort of differences of these anomalies along the seasonal curve. So what about spring and fall? Well, now we're working through our seasons here. What about these kinds of anomalies? Does variability impact, temperature variability impact health? this has actually drawn my attention probably the last decade or so in terms of some of the research I've been doing. It's a really interesting topic and it's complicated. But I'm going to talk a little bit about variability now. The paper that we put out a couple years ago where we were looking at emergency department visits, University of Virginia hospital, okay? And I'll talk about how to interpret these plots in just a minute, but the colors here, just think of the colors. Red color is more deaths, blue color is less deaths. This is a plot of diurnal temperature range, that's the day-night temperature difference over a 24-hour period, okay? Versus lag, okay, there's that lag factor. And here you see in the cold season that we have peak deaths sort of on days that have diurnal temperature ranges that are high, sort of above 20 degrees or so. And so we can look at the weather on these days and we find that in the cold season, these are tended to be cold Arctic outbreaks that are associated with clear skies, very cold days, cold nights, low dew point temperatures. So the dew point will drop very low at nighttime. But interestingly, when we have them in the warm season, we see the same kind of response. It's even much stronger in terms of the mortality. What are these days like? Well, in a place like here in Delaware, sort of May or October, these are days where the maximum temperature is below 80 degrees, low humidity. These are glorious days. These are the days you dream of. This is San Diego weather, right? It turns out that there is a mortality peak, or excuse me, an ED visit peak a day or two after you have those days in the fall and the spring. It's fascinating. I didn't believe it's true when I started going into this research. I'm like, I'm going to disprove this diurnal temperature range garbage. And I keep finding the same results, right? So that's research. I like that because it challenged my own ideas about what I thought was going to be the truth. So one of the theories here is that this goes to the whole acclimatization topic that I was talking about before. There's something called the acclimatization thermal strain index, okay? A stress is when there's a net thermal load on the body produced by the external environment, whether it is like extreme heat or cold or dry air or whatever. The strain is the effect of that thermal stress and the consequences of it on the body. So clothing can change the flux of the body. Obviously, in the wintertime, you dress up, you wear sweaters, etc. But your respiratory system is always unprotected. So we're all inhaling air. We're inhaling air at whatever the ambient temperature is. We exhale air. Our body warms it to core temperature or close to core temperature and also humidifies it. It all happens in the process of breathing in our lungs. So there's a strain placed on our respiratory system every time we inhale temperature that is different from our core temperature and has a different humidity. And you can actually do the calculation of what the heat stress exchange is within the lungs based on sort of external temperature and humidity. And I can show you that, but I didn't want to have that slide in here. And so and it turns out that the only unprotected system in the body, of course, is the respiratory system, and it can account for a lot of the heat loss that we have. So here's some numbers. Respiratory system in cold conditions, your bronchia can constrict, resulting in less volume in your lungs, right? So now you need more oxygen, but you can't get it because of this constriction in cold weather. So this produces a physiological strain on the respiratory system that can also affect the cardiovascular system. And you have to either become acclimated to less oxygen, and people who do, of course, you can think of Sherpas, for example, that are used to this. The breathing rate changes, they have more mucus glands, and their heat loss is reduced compared to unacclimated people or non-acclimated people. The respiratory system can account for up to 50% of the heat loss in the body. Typical values are less than that. So you get the idea here is that we can put as many clothes on as we want, but you can't protect your lungs because you're going to have to breathe in the external air. So this index accounted for changes from hot, cold, and humid to non-humid conditions, okay? So if we think now we're talking a little bit of climate here and weather changes within a season, such as a frontal passage, cold front or warm front passage, would be associated with this thermal strain index, right? And so it requires short-term acclimatization of your body to these changes. So for example, let's say you're in the middle of winter and you get a hot spell, like in February or something. Well, boom, that's going to be a high value of the ATSI. Or in the, like we're getting now, we had a long period of warmth, cold slam. Once again, acclimatization needs to take place. So the thermophysiological impact or strain that results from the lack of your body's acclimatization to the new weather condition that you've experienced. So we looked at hospital admissions for respiratory diseases at UVA. We plotted it up by month. And what's interesting here is that we see September shows a peak in terms of the admission Z-score, which is at, of course, like same climate as you have here, sort of late summer, early fall, right? If we looked at plotting monthly admissions versus the ATSI, here's that index, right? Negative values are associated with warm, humid to cold, dry. Notice where all the high values are. September, October, November, on those times when you're going from warm to cold, and we have to go through this adaptation. So I know what you're thinking. Looks suspiciously like the constellation Canis Major, right? And if you know, you know. Okay, so we went on to look at this question for, like I was talking about, respiratory hospital admissions at UVA, and we're now once again looking at the lag question. On the day of the cold transition or the warm transition, we find no relationship whatsoever. It's not an immediate response. However, when we lag a little bit, so I'm using different smoothers and lags here, like I was talking about before, we see a peak when a cold and dry week follows a warm, humid week, respiratory admissions increase. Okay? So warm, humid to cold, dry gives us that additional thermal stress that could be related to these increased hospital admissions. And then when you get to very longer time periods, we see an even stronger relationship. So this is saying the longer smoothers reflect the increase in respiratory admissions in autumn. So now we're getting to the point where we're just really looking at seasonality here in this relationship. Now, finishing up fairly soon, you're getting close, but I want to talk about the way people in the medical fields refer to that sort of response variable. They have different statistics, one of which is the relative risk. And I'm going to be talking a little bit about relative risk in my last few slides here. And you can say you have some potential stressor, a weather event, a hot day. Is it a hot day, yes or no? Do we have the response of ED admission or mortality, yes or no? You count the numbers in the boxes. And the relative risk is the ratio of the risk in the exposed group to the risk in the unexposed group. So it's A over A plus B divided by C over C plus D. And the way we interpret a relative risk would be that if the value is greater than 1, then the risk in the exposed group exceeds the risk in the unexposed group. So that means there's an added risk. If it's below 1, that means that it's what we would call protective. There would be less than expected deaths or ED visits or hospital admissions or whatever. So relative risk 1 is the standard. Higher is higher risk. Less than 1 is lower risk. So we recently completed a study for the entire state of Virginia looking at mortality over a 16-year period, about 1 million mortalities with sort of patient level information there that you can see. We divided the state up into different sort of districts and had an associated weather station to sort of get the climate for each of these locations. And what we did in terms of the modeling here is we're using kind of a time series approach, something called the generalized additive model. I'm not going to get into the details of this, but I obviously can do that if you want. But what we're looking at is here's an example of the equation we used for one of the locations. The log of the response variable, this would be mortality here. And so this is going to be a Poisson regression because we're dealing with count data. And it's really common in health studies to use sort of a Poisson regression approach. And it's called the log link function. So we're tying, this is like a multiple regression where we have a bunch of different predictors. There's an intercept term, and then we have various climate and non-climate predictors that can be related to this log of the death count. And so there will be a trend term. What we're going to do is we're going to try to remove the seasonality in the long-term trend with that term. We're going to then, and here's an example of doing that. And this is an example of some data I had where you want to, so here's the gray dots are showing our day-to-day sort of time series of mortality, right? And in this term, what I'm doing is I'm fitting a smoother or splines through the data that are trying to account for the general overall seasonal patterns, right? Using as few change points, as few knots as possible. So this is an example of what I would say is a good fit. What we're trying to do is leave the remaining variability to be accounted for by climate variables. On the right, this is an example where we have too many degrees of freedom added, and we're doing what I would call have an overfitted model where we're trying to account for all kinds of little fluctuations in the data. Of course, if you add enough degrees of freedom, you can connect every point. You're not going to prove anything, right? So we want to keep it as simple as possible in that term. Then we're going to look at things like we have nominal variables, day of the week. People don't like to go to the hospital on the weekends. They like to wait till Monday. They don't like to go on Fridays and holidays, et cetera, right? We have a factor for heat waves here included. And then we have, of course, our climate variables that we can, in this case, we have maximum temperature and diurnal temperature range as our potential predictors. So the coefficients here, B and C, turn out to be what are the log odds of a unit change in the predictor. And if it takes the exponent of these, turns out that these values are the relative risk. Okay, really interesting, and you can learn that in an epidemiology class, but that's the way that math works out. So what we're doing here is we're trying to use these predictors to account for mortality in Virginia. And in this particular study, we did it from day 0, which would be the day of the weather event, to 3 weeks afterwards. And here's the results we got from the GAM, okay? You can see in this case that we're seeing a really significant cold response and not very much of a heat response. So the way we would interpret this is that, let's say at -2 degrees C, if that was the maximum temperature on a given day, you can see the relative risk is 1.1. So if we compared that to the median value, which is about 15 degrees or so, what we would say is that when the high temperature on that given day is -2 degrees or less, then the relative risk of mortality increases by 10% over that day and over the next 3 weeks. Okay, and so in this case, we found a sort of a strong cold response in Virginia based on that particular model. Heat is slightly protected. You can see that sort of just a little bit below the mean value there for heat for Virginia. Now, what we can then do is we can say, all right, how is this going to change over time? So if we think of this was an average over 21 days, now let's break it out in the third dimension and look at the lagged response. So now we're running what's called a distributed lag nonlinear model, or DLNM. If you read any sort of these health and climate papers, everybody's running DLNMs these days, okay? And it's very popular and it's a very high-powered way to do this. So what we're doing now is we're looking in that third dimension and we're going to fit splines in this direction so we can count for the immediate response and the lagged response over time. So we get a result that looks something like this, okay? Here is the distributed lag nonlinear model for Virginia. Lag is our y-axis, maximum temperature is our x-axis. The colors here are the relative risk, reds being higher risk, blues being lower risk. So what do we see? When the temperature is above 20, certainly when it's above 30 degrees for the maximum, you see an acute heat response. 0-day lag, 1-day lag. On the day of the heat, you're seeing a mortality response. And the lag is not long. It's only a day or two. If it was hot today, 3 days from now, your body didn't care about that. It's lost any remembrance or memory of that event. Look at this blue blob right here. What's that? That's mortality displacement, right? These are the people that died from heat. Now, 5 to sort of 7 to 10 days later, there are fewer deaths than we would expect because of the displacement effect. At cold, notice how the response is completely different now. You have an acute response, but then you have a long lagged response. Is this related to pneumonia and influenza? Probably at least partly, right? That cold, dry conditions in the winter and the longer lag response you see in mortality. So there's both an acute response and a lagged response. You see completely different response at the other end of the curve for heat. We also compared white versus black Virginians to sort of look at the racial disparity effect here. And we have a paper, it should be just, we're just resubmitting it, and I think it'll be coming out next year on this. So you can see the white response here on the left, the black response on the right. And just to show you a couple of the differences we see, cold relative risk is higher for blacks than for whites, right? You can see there versus there for the same temperature. -10, it's a little over 1.1. For whites population, it's just a bit over 0, right? 1.02. And then the heat in Virginia tends to be protective for the white population, but not so much for the black population. And you can obviously think of some of the obvious reasons why that would be the case. We looked at other diseases just to give you a sort of a feel for some of these things. Renal or urinary tract data for Charlottesville Hospital. We find a heat response that is quite clear for kidney-related diseases. So the heat results in dehydration, that's electrolyte loss. Electrolyte loss can result in kidney stones, acute kidney injury, chronic kidney disease, things like that. To the right, we did a study for diabetes in Rona. We were just talking about this at lunch briefly today, right? We're seeing a heat response, pretty commonly known with diabetes. Blood viscosity, impaired sweating response. When it's hot, diabetics have a hard time cooling themselves off via sweating. However, we got a little bit of a actually fairly strong cold response that we haven't seen a lot of in the literature. The shivering response is impaired, and there's some hypoglycemia, which affects diabetes patients, right? So once again, kind of a different response for heat and for cold. So this is what our tour de force of the 4 seasons over the last 45 minutes or so, right? We have high anomalies in the winter during the high mortality season, some of which are related to pneumonia and influenza, which are tentatively linked to cold and dry air and deaths that follow sort of 2 to 3 weeks after that. In the summertime, we see heat-related mortality. We also see mortality displacement. There definitely is a heat impact, but what the total heat impact is, you don't really know until you consider both of those factors. Physiological strain related to seasonal changes and going from hot to cold, cold to dry, dry to warm, dry to humid, etc., from fall and winter. And so we see those kinds of changes in the shoulder seasons. And so that is me. This is my email. So many people to thank over the course of doing this research over many, many years. So I'm not going to try to do that, but it was my pleasure being back at Delaware. I mean, it's just great to be back here. And thank you all for taking the time out to see my talk today. I appreciate it.
Thank you so much, John.
By the way, if you want to send me an email, I'm happy to respond to you. So, all right.
Thank you so much. This is great. Methodologically so rich and very relevant on a day-to-day basis.
There's a lot of stuff I threw at you. I know.
Thank you so much.
Thank you.
Okay, wonderful. Now let's open it up for Q&A. We have about 10 minutes. So first from the floor, but
response have you had to your research over the course of time, particularly from hospital staff and that sort of thing, or individuals who heard of what you've concluded and said, how can I adjust myself to your adjusting?
Yes. Well, one thing I always tell people, I think especially for the elderly, if you're in a middle or high latitude climate, that when you're warming your home in the winter, you have to humidify it. Because by not humidifying it, you're just endangering yourself. I mean, as you know, flu is particularly deadly to people over 65, right? And so that's something that you can do, and that a lot of people don't do, is worry about the humidification.
Have you found any correlation between people who've responded that way and people who haven't?
I don't do that kind of research, that goes down to that level.
Yeah.
I'm dealing with more population scale. But yeah, that's kind of one of the messaging things that we like to get out there. In terms of, the obvious ones to heat, you hear about all the time, don't run in the middle of the day, try to do your work in the morning and the evening, stay out of the hot sun, that kind of thing. I think the messaging is out there. Mostly at this point, it's, dealing with, the homeless population, the indigent, people that are, working in jobs that result in them, if you're a roofer or construction worker or something, there's no way to avoid it. These are the people that tend to be most influenced, and also, people that have lack of air conditioning. I mean, it's very straightforward in terms of a public health perspective that air conditioning saves lives, right? Yeah, there's an electricity demand cost for that, but it's undeniable that if you keep your body cool during a heat wave, that your chances of not getting sick or dying are much higher.
But the energy cost for heating is far more than cooling.
Yes, it
actually.
is, yeah.
Far more.
Yeah. And, we need the heating more than we need the cooling, because our body can, as much as we don't like to admit it, our body can deal with the heat better than the cold. So, yeah, thanks, Peter.
Great. Questions on Zoom, feel free to chime in as well. Others from the floor, but we have a couple of students who are working on geo-health issues as well. So, down the road. Yeah, that's an area within the department that, only recently we've started to re-engage with, thanks to Dr. Levy. Otherwise, and we do have a health science program. I sent your announcement to health science.
Oh, okay, good, yeah.
We don't have a medical school, but we have health science.
Yeah, that's good, that's good.
So,
What about this fellow we used to hear about, Larry Coxton, I believe? Now, Larry was big into using policy changes. He was advocating to public health institutions in different cities around the world.
Still is.
How
Yeah.
that, does any of that I mean, when you first started and you were talking about the cold is really the problem, and the heat we can sort of more or less deal with, and I'm saying to myself, well, I bet that shoots Larry Coxton.
Well, I never worried about pleasing Larry, we were he was my major professor here.
Yeah,
We were loggerheads on occasion, but it was still fun. In fact, I still see him, every year or two, so, yeah, I see him around, but, yeah, no.
Would you say your research
Yeah.
has basically superseded?
The way I look at it is, it's a U-shaped relationship. You're gonna have cold effects, you're gonna have heat effects, right? There's no doubt about that. It's tricky research because we're not dealing with middle of the distribution at all, where all the data are. We're dealing with the edges of the distribution, where there's fewer data points, and it makes it really complicated to kind of do the research, but also kind of challenging and fun. But yeah, heat obviously has gotten more sort of public attention because of climate change and everything like that. But you can go through the literature, and there's paper after paper showing that the cold effect is much stronger than the heat effect in terms of the body's adaptation. And it just makes sense the way we are, the Homo sapiens have evolved over the period of, many thousands of years, right? To evolve to be able to deal with heat better than we
And
can
yet we
cold.
don't have the same public health announcements about cold temperatures that we do.
But I think that's because it's not such a straightforward acute relationship. I mean, a heat wave comes along, boom, that day people are in danger. But in the wintertime, it's cold, it's like, oh, I just, stay inside, right? I'll bundle up or whatever, and then I don't have my humidifier going and I get flu, right? And then you die. So, yeah, it's just a much more complicated, the evolution of disease during cold conditions is much more complex than the heat response. The heat response is too hot, high core temperature goes up, I don't sweat enough. Elderly people in particular have a diminished sweating response, and so it's even harder for the elderly to stay cool. And so I think it's just a much more complicated story.
One thing, this might just be an old tale. I don't know if there's anything true to it or not, but I've always heard that, a lot of people don't want to die during the holidays or something like that. So that's one of the reasons that you'll see January 2nd or 3rd
Yeah.
is what
It's true.
you see it. Do you think that?
Yeah, we put a holiday term into our models.
Yeah, I saw that there. but
Yeah.
How significant was that?
It's small, but it's there. I mean, you'll see the data and you'll say, okay, we're gonna put Christmas Day in and your Christmas Day has a lower death rate, but then, 2 or 3 days later, it goes up.
Okay.
Yeah, and you see that particularly for Christmas and New Year's. You don't see it so much for like July 4th or Memorial Day or whatever. It's like, I gotta make it through Labor Day. That's a
But they're not cities.
What?
But they're not cities.
Well, whatever. That's another issue. I wish we could stay to, I would just stay in daylight savings time all the time. In fact, I would keep moving the clock, so I hate like dark all morning, I don't care.
But-
I like my late afternoons and evenings.
But there was the whole debate on
No,
why
there-
they
there
didn't do
is.
it. It was because they said sleep deprivation
Yeah.
is the problem.
Yeah.
And then sleep and mortality, apparently there's very complicated relationship.
Yeah, there are some studies on this. I'm not poo-pooing the studies
Yeah.
entirely because obviously our sort of sleep schedules and our work schedules change.
Yeah.
But yeah, it's twice a year you hear about it.
Yeah,
And then everybody goes back to normal life.
our state
Yes.
meteorologist, yes.
So Bob, I'm curious, the temperatures that you came up with that sort of show that that's the trigger point where you start to see
Yeah.
the mortality rate go up. Have you seen that temperature threshold shifting over time?
Yeah, we looked at that too. Yeah, that was one of the papers we looked at, that threshold is actually in a number of cities changed through adaptation. So that's kind of a measure of acclimatization of that population in that particular location. So in that series of papers, one of the ones we looked at was sort of changes in threshold. And I should mention that original paper on that was a couple decades ago, but other research groups have followed up using different data and they've come up with sort of similar results. So I think it generally seems to be the case that heat-related mortality is declining and maybe flat. We might reach a point where we've saved as many of the easy lives to save, and now we're left with the difficult ones, the people that are exposed, indigent, homeless, etc. So, yes, sir.
In addition to the temperature, have you looked at the precipitation extremes, like, because in the cold winters, we have also snowfalls in some regions?
Yeah, I have not done that. There has been some research on that topic. That's just not something I've delved into. Yeah.
Great, thank you so much, Bob. We're right at time. This has been fantastic, great learning experience for us all. And we hope you will remain connected with the department now that you're back. You have seeing what
Great.
we're up to here. We have PhD students. We have now 2 PhD programs, climatology and geography.
Fantastic. You have
Thank you,
PhD in climatology?
Yes, yes,
Good, I love it.
absolutely. We
All
have
right.
new climatology faculty. Our newest one, Dr. Kelsey Malloy, who's just joined us from University of Miami. And so,
Great.
yeah, wonderful. I
Thank
hope
you.
you get a chance to mingle a bit.
Fantastic.
Thank you.
Thank you. Welcome to Delaware. How long have you been here?